record this presentation so that we have it for purposes in the future. So first of all, let me see if I can show the screen live. It's not coming up. Projector. Not projector. Oh. Let's see if this works. So in the meantime, I'll share my desktop screen. Oh, sharing the wrong screen. Huh, this. This here. Okay. Just to clarify, which screen are you seeing? Francesco?
It's an IDE, now it's a browser.
Okay, awesome, perfect. So before we get started, I think a great thing what we should do is to see at the end of this tutorial. First of all, hi everyone. By the end of this tutorial, I want to show you guys what you're gonna get, right? So we're gonna start off with what we're gonna get, and then the whole class, this whole tutorial is basically how to actually get there. As you will see, by the end of this tutorial, I'm going to have turn off my emails. I will run a 737 tutorial, and by the end of the tutorial, we'll be obtaining some parameters. So basically, here's on this side. By the end of this tutorial, we're gonna get all of these plots. I'm just pulling them from the next my next screen here, and I'll talk about these plots in a second. Okay. Good. So by the end of this tutorial, we're gonna model a 737 aircraft in RCAIDE. A very simple tutorial. It follows similar to SWAV. So if you guys have used SWAV in the past, that is great. We're gonna cover a little bit. We're gonna finish the installation, and then we're gonna cover tutorials. Right, this one tutorial. If you're having trouble with the installation part, see me afterwards, and I can help with the installation. But the most important thing is understanding the tutorial and how things are integrated. Does that make sense? Cool. So by the end of the tutorial, we're gonna essentially run a simulate a 737. The 737 tutorial is actually already on GitHub, so you can find it. If you go to our lab's GitHub repository, you download tutorials. If you have the code and you have the tutorials, if you press run on the 737 tutorial, it should run this, and I'll tell you which one to run in a second. But basically, these are the results you're gonna get. A whole bunch of results. I'm not gonna go through everything, but you can get stuff like the different drive components for the different stage of the flight, and you can see the different stage of the flight over here. You can get the throttles. You can obviously see a top of climb requirement, basic top of climb power setting. The weight of the aircraft. This aircraft is burning Jet A1 fuel, so you can see obviously the weight of the aircraft is changing. You can get the specific fuel burn. You can get aerodynamic properties. This have been validated by, I don't know, several different places, Ryanair, Embraer, you name it. So these are pretty standard for the 737 aircraft. We don't do any stability. We're not going to model any stability in this simulation, so we just have it at 0 for now. What else you can get? A whole bunch of other things. So I'll let you guys explore that, the power, the lift, etc. And also this is the altitude plot. So this is the actual trajectory of the aircraft that you're simulating, right? This tutorial right now I'm gonna spend most of the time explaining how to actually design an aircraft and what are the key changes that have been made since the soft release of RCAIDE But the final release, you guys know already. In Las Vegas, you'll see the product, and Francisco and Nermit, for you guys, my undergrads are working on a very cool GUI, so I'll keep you guys posting on that. But also, in addition to that, one of the things that we're doing in Arcade differently is a lot of visualizations, right? So we want to make sure that you actually see the aircraft that you are simulating. So all of this stuff is going to be essentially housed in the GUI when we finish the GUI. But basically, this aircraft is a narrow body mid-range aircraft, the 737-800, I believe, without the winglets. But you can see here, if you zoom in here, you can see there are like slats. And if you look right here, there's like we model slats and a whole bunch of other things that can change the settings, right? So this is where we're going to end up today. Any questions? Okay, so before we go into anything, by a show of hands, who has Arcade downloaded and installed, right? So last week we covered installation. Sorry, we covered downloading the files from GitHub, but also we need to cover installation. So who has installed Arcade? Okay, most of you. Who has not installed Arcade? Okay, cool. So basically, for the installation, it's a few quick steps. So I'll just leave it up, and if you go to our lab's website, go to software, and you go to download. Essentially, these are the steps here to install Arcade, right? So currently speaking, and like I said, I will breeze through this quickly because I really don't want to spend a lot of time on the actual tutorial because that's very valuable. But after we can talk about this. So basically, to install Arcade, we need a few different packages. So first of all, you want to make sure that you have Python installed, and pip. Pip is the installation package that we're going to use to install pretty much everything else. So you have pip installed NumPy, SciPy, version 1.7.3. And the reason it's 1.7.3 is because SciPy has a bug in it, and I've been emailing them to correct it on the integration, and they haven't responded to me as yet. So basically, there's a bug in one of the ODE functions in their newest version of SciPy. Matplotlib and Plotly for plotting. Currently we support both, but in the future we're going to have one. Kaleido, Pandas, scikit-learn, and GeoPy, because we do a lot of noise modeling and different types of modeling of different environments in the world. And then once you have these packages, then you guys have already done most of this already because we've cloned the repository. The only line you need to do is the actual installation, which is Python 3 setup .py develop -- user, right? Or just setup.py. So that's the only line to install Arcade. And then you're pretty much done. And that basically you're taking the files that you have downloaded from your GitHub repository and just running the installation. So, like I said, if you guys have not done that already, I will skim over that right now, but just pay attention to the screen because there are a lot of fundamental changes that are very critical to that are unique to Arcade, right? So before I do that, I want to first talk about we're gonna now go into the vehicle simulation. But before I talk about the vehicle simulation, I'm gonna share with you guys a paper that we're writing, myself, Professor Ansel, Professor Smart, Professor Krygos from another university, University of Illinois, and a few other research engineers on pretty much Arcade, right? So this paper is going to be published, is our seminal paper, right? Which is a paper that covers what Arcade is. But in that paper, I talk about the energy network, which is completely different from if you've used SWAV before, completely different. The purpose we did this was basically because we are discovering from our user base that we need to have the ability to model very unconventional energy networks. So what we did is that we asked a whole bunch of people, but we took the approach of trying to model an energy network as similar as a realistic propulsion architecture. So what are the things I'm gonna talk about right now basically reflect the elements on an aircraft. For example, if you have a fuel burning aircraft, you have something called a fuel selector, which essentially allows you to manipulate the fuel flow between fuel tanks, right? So there's a lot of things that we're doing right now that allows us to do things such as hybrid propulsion architectures and different, I mean, Edwin knows this, but different types of hybrid propulsion architectures to a level of fidelity that you can do stuff like really understanding the impact of failure design conditions. Okay, so I'll share my, I'll see if I can find it first. Ah, there you go. So the paper is currently in under, I guess, AWA review, which I am a reviewer myself, so you know, hopefully they also accept it. Anyway, but basically, I want to show Francisco and Nermit, can you see my screen?
Yes, we
Okay,
can.
awesome, awesome. So the biggest thing from what separates RCAIDE from honestly every single tool there I've seen so far is how we're going to model these new energy networks, right? So, and this is very relevant for the folks who are doing the GUI right now. So what we're doing is that we're essentially we're breaking up the energy network into more realistic components, right? So you have something called a propulsor, and a propulsor is pretty much a class, right, that contains elements or components that generate thrust, right? So a propulsor right here, as you can see, and I did it painted in the back. A propulsor, for example, is a turbofan engine, right? Or a propulsor could be a motor and a propeller combined, right? That combination provides thrust. Does that understand? Do you guys understand that? Cool. A fuel selector is a device that pretty much essentially varies the fuel flow, right? So if it varies the fuel flow or changes the ratio, you can assume that that fuel selector can be defined as some type of ratio, right? So we have a term now called fuel selector ratio, right? Then we have the ability now to model multiple fuel tanks on an aircraft. And this is something that some of our the companies wanted the ability to essentially, for example, if you have a Concorde, right? A Concorde actually has 9 fuel tanks. We want to be able to model those 9 fuel tanks and determine, how does this aircraft stability change when the fuel tanks are being burned? How can you move fuel from one fuel tank to the other? These are some things that were not possible in SWAV, and that's how we try to address those things in RCAIDE. But it can do a lot more complex things now, right? Oh, sorry. Before I actually go on to this one, the last thing that we did in RCAIDE is that we decided, you know what? We need to find a way to connect the fuel tanks and the propulsors that share similar energy flow. Let's call it energy flow. And we call that a fuel line. And if you look on an aircraft, typically speaking, aircrafts have a fuel line, and on a fuel line, you can have multiple propulsors and multiple energy storage devices, or in this case, fuel tanks. So a fuel line is pretty much what we call a distributor, right? You can think of it as a distributor that distributes fuel it takes fuel from all these different fuel tanks, distributes it, collects them all together in one line, and then essentially distributes it along to the various propulsors. Does that make sense? Cool. So far I've covered propulsors, I've covered distributors, and I've covered fuel tanks or energy storage devices, right? So there are three different classes, right? So the fuel selector, you can think of it like a modulator, right? Some type of modulator. Anyway, so for an electric architecture now, the interesting thing about how we model electric architectures now is that because we are using now the idea of a distributor having multiple propulsors and multiple energy sources, now for the first time, we can model multiple distributors. For an electric aircraft, these are called buses, right? So in the same way how a fuel line, the equivalent of a fuel line in an electric, in a conventional aircraft is an electrical bus, right? And that allows us to model a system where you have batteries, multiple batteries, powering propulsors on a particular bus, right? So in this system, how many buses do we have? Anyone? 3. We have 3 buses. I just color coded it just with a trick question, right? We have 3 buses. Now, I'm not modeling anything with regards to certification. Realistically, what happens if you're trying to certify an aircraft is that there are actually hidden lines that will say connect this battery to this motor as to this propulsor as well, right? So if you want to take this nominal aircraft and really redesign it for certification, which some of you guys are doing, essentially there are going to be multiple, like you can call it like a hidden bus that will essentially become active when, let's say, a battery or a particular bus line fails, right? So that's just the FYI. I'm not covering certification here. Okay. Another thing that this allows us to do, this separation allows us to do, is pretty much we can now combine for the first time buses, which are electrical buses, which are electrical distributors, and fuel distributors, right? Or fuel lines, right? And this allows us now to do things such as modeling hybrid architectures at a higher fidelity than simply just having like a what I've seen so far, which is like a hybridization ratio, right? It's not doing a hybridization ratio anymore. We're really actually capturing how these different components work. Okay, so that being said, that's just the architecture, most of the architectural changes within RCAIDE on the energy network side. The folks are, the other folks were really happy about how we define stuff. So we really haven't changed much on the front end of that, but there's a whole bunch of changes we made under the scene to the mission solver, how missions run, which I won't cover in this particular tutorial right now. So that being said, I'm going to open the 737 tutorial and actually look and talk through how the different components in there are actually parameterized. Okay, cool. That's the FYI. All right. Any questions so far? Okay. So this is the 737 aircraft. And like I said, the location of the 737 aircraft, if you go to GitHub, you go to GitHub and you go to, well, right here, if you go to Lee's group, you can pretty much see the tutorials here, RCAIDE tutorials. And in the tutorials, we have a lot, and I'm still working on more of them. I'm also updating them, but you have here stuff from airfoil analysis to propeller analysis to a full vehicle polar. If you want to do drag polars for a whole aircraft, you can do stuff like 737, which we're going to do right now. You can do a 737 with AVL. You can do a Cessna, a UAV analysis, General Electric aircraft, an eVTOL. You can do the Concorde, solar UAV, a whole bunch of tutorials which I've made over the years. Well, not only myself, but other folks. Professor Smart did some other folks did some. Control surface sizing, a whole bunch of stuff in here, right? So I'm always constantly updating them and making sure they're working and etc. But we're gonna do the 737 tutorial right now. So, like I said, if you haven't downloaded RCAIDE, that's okay. Pay attention, and then we can quickly download it afterwards. But this is more important. Okay, so for the 737 aircraft, basically, there's typically for any aircraft, when you're doing a mission simulation, you have a main function, right? This main function that first you define your vehicle, then that vehicle is used to create vehicle configurations, right? So you first define your vehicle, then you create vehicle configurations, right? And the reason why we want to create vehicle configurations is because let's say you want to define your aircraft, right? You just define your aircraft that is. But let's say you want to model now in one particular flight segment, like a takeoff. Let's imagine now the flaps are actually deployed. Why would you have to design the whole aircraft again? You don't want to, right? So what we do is that in that configurations function in line 35, we pretty much take that vehicle and make copies of it, and then change maybe the flaps in certain configurations, and we define that, let's say, an aircraft takeoff configuration. Sorry, the 737 takeoff configuration. And this allows us not to have to design 5 different aircraft because we have maybe 5 different types of flap settings for the aircraft itself. Does that make sense? So we set up our vehicle, then we make configurations of them. Then we append the analyses to the configurations. What are analyses? Aerodynamics, weight, stability, noise, etc. Basically, we're in that analysis setup, we're pretty much determining or defining what types of analyses are going to be run on these configurations in flight. Okay. Once we have our analyses, we're just going to then now set up a mission, right? So now our mission is where we define, let's say, all of the different climb segments, all of the cruise segments, and the descent segments. And basically, for each segment you define, you can then append to that segment the particular configuration that you want to study. Does that make sense? So Dyer, this is very important for you, right? So basically, you know, if you're creating a takeoff segment, you use the takeoff configuration to append to that segment. So when you're simulating your whole aircraft, RCAIDE knows that at that particular segment, we're going to use the takeoff aircraft with this flaps deployed. Okay, so once you have your missions, then similarly, similarly, you can define multiple missions. So the same way how we have a config setup, the mission setup is similar. So the missions plural setup is similar because what if you want to study a family of aircraft and how they perform? This is something that Embraer really liked. Basically, you can define several different missions and maybe change the range, right? So you can study one aircraft with different configurations on different missions. And this allows you to do some things such as, you know, market analysis, right? For example, if you want to define a mission from JFK to LAX, then maybe a shorter one from Dallas-Fort Worth to SFO, right? You don't want to have to define the whole mission again. You just use the mission you have and then change the cruise, right? Make sense? So once we have our missions, then we evaluate it, right? And that's that line 47. And once we have evaluations, then we just plot some results. So that's the main function. Any questions so far? Cool. So, not to spend too much time on the functions that are really not really relevant to you right now, because you guys can read this, but like I said, the analysis setup, this analysis setup here, this function here is located right here. And what it does is that for each configuration, it appends all of the analysis you want to run, right? That's just for a loop. For each configuration, you append the analysis, right? And we call that analysis, that's defined as base analysis. You can define it whatever you want, but we define it as base analysis. And in base analysis, let's see what we run here. We run a weights model, which you use I think this is the TASOP weights model, but you can actually determine if you click on the function, you can actually determine, it should give you a source. If there's no source, it's probably something. Oh, I think it's flops. So we actually use flop weights in here, which is another analysis. But basically, here we do weights analysis. We use a subsonic vorticestatic method code. We do the energy analysis to determine how much energy is being used. We assign a planet because Professor Crow at Stanford and some folks actually, instead of using US standard atmosphere, you can use like Mars atmosphere if you want to study eVTOLs on Mars, like if you want to study the ingenuity, right? You basically just change line 115 to change the type of atmospheric model you're using. Does that make sense? Yeah, and that's pretty much all the results. I mean, all the analysis. Like I said, I didn't include any noise in here. I didn't include any stability, but you can also add those types of analysis methods, right? You want to run. So I guess for the folks at Argonne, here would be a place where you would put your life cycle analysis, right? You just append it onto the analysis being run such that now you can know through each segment, you can understand maybe the emissions or emissions produced or any other quantity you want to evaluate. Okay, so the biggest one is the vehicle setup, right? That's the, according to Professor Ansel, that's the meat and potatoes, right? He always says that. So in the vehicle setup, some of you guys have already know how to set this up, but for those who don't, we define a vehicle. So the way how RCAIDE is pretty much a bunch of classes, right? A Python class. A class is, for those who don't know, the data structure that you can store functions as well as other types of data, right? So we have a class called vehicle class, and we first name it, call it using a tag, right? Vehicle.737. And then you can see here, we define some high level properties. So we have the takeoff weight, the max takeoff, the operating empty, the ultimate load. And if you guys were in my flight mechanics class, you can see here the ultimate loads, the N factor 3.75 and stuff like that. The number of passengers and a whole bunch of high level parameters you can input here, landing gear, etc. And then now starting from line 164, we are defining our first wing, the main wing. So here, one of the good things about RCAIDE is that you can define a wing at varying levels of fidelity. Or what I'm trying to say is that you can define a wing with a basic number of parameters, or you can make it more complex, depending on how far you are in your design stage. So for the wing, for this main wing, we have the parameters such as aspect ratio, quarter chord, thickness, taper, all the different parameters of a wing. We also make sure that it's a high lift wing, so we put that high lift as true, and it's not a vertical wing, so we just have it as false, right? So those are the simple parameters that if you were to use, if you did nothing else, this will be sufficient for creating a trapezoid that you can put into the VLM that actually works like a wing. However, you can define a wing even more by wing segments, right? You can add control surfaces. So we define here different segments. So you have the root segment, where you have stuff like what's the percent of the chord to the root chord. You have what's the segment sweep, the segment span. You have the root segment, the Yehudi segment, and just the section 2 and the tip. And if I were to go back to my diagram, this is pretty much the root segment in here. If I can rotate this, yes, nice. So you have here, this is the Yehudi, this is the root segment, Yehudi segment. So that's just one segment. You have this segment here, and then you have the tip, right? You can increase the resolution of your definition of your wing. Does that make sense? Cool. And then, yep.
Division the parameter, that's the modulation.
Hmm?
Division the like wing parameter, that's the modulation.
Wait, could you repeat that?
Division the parameter here,
Yeah.
so that's the modulation.
Yeah. Does the model? Yeah. And then you also can define like stuff like the control surfaces, right? So essentially, these are control surfaces that actually are for the entire wing itself. So we already have written scripts that it goes through the particular segments and actually breaks it up so that you can define the control surfaces. So you have a slat, a flat, and an aileron. Okay. Okay. So you have that's the main wing. You have the horizontal stabilizer, which is another wing. Just define, arcades.components.wings.horizontal tail. And similarly, we can define segments for that. 2 segments. We have the elevator, which is the rear wing on the aircraft. I should bring my Lego model. I always use it in class. And then we have a vertical stabilizer. Vertical flag is no true, but similar definition for the different segments, and then also the for the different segments, right? So that is the wing definition. So I've done the vehicle high-level properties and also the wing definition. Cool. All right. Then the next one is the fuselage segment. And similarly, like for the fuselage, you can define it using a basic level of parameters, or you can actually increase the definition. So the basic level parameters are shown from lengths 420 to 441. And I just have here the length, the width of the fuselage, how many seats abreast, the 6 seats on the 727, the one ABC, the row, DEF, knows before. The seat pitch, which is 1 meter. I don't think that's anymore, but I think we don't have a lot. I think that's not correct, but seat pitch, and some whole other parameters you can define, right? But similarly, if you notice that this aircraft, right, this 77 aircraft, it's hard to see, but this has a very nice, interesting curved shape, right? If we were to actually cut this into cross sections, I have actually defined what is the radius and the height of each of pretty much cross sections along the fuselage to get that nice aircraft looking shape, right? If we can rotate it a bit more, essentially, I've essentially created segments, fuselage segments along here. If you look carefully, and you can see where the segment changes, right? So basically, I can also have definition in my fuselage. So if you're doing stuff like eVTOLs now, right, you can actually design some really cool fuselages because you have the ability to modify the cross sections, right? And that is done by appending segments. So each segment has the X and Y location, right? And then it also has the height and the width, right? So you can define new segments. And I'm also working behind the scenes to actually define different types of segments, right? Like open VSP. So not only elliptical segments, but imagine if you want to do like a square cross section or any type of cross section, we want to be able to do that in our code. Okay. So different segments, many different segments actually. And then at the end, this is how you define a fuselage. So once you define your fuselage, similar to wings, I forgot to mention this, but once you define your fuselage component, you just append it to the vehicle, right? Because your vehicle is like a main class, and you want to append, you create a wing and then you append it to your aircraft. Append means just add, right? You create a fuselage, you append it. So you're just appending, you're defining stuff, and then you're appending stuff to your aircraft. Make sense? You guys already know this already, but this is a refresher for y'all. The energy network is actually something that you should probably pay attention to. So another thing we want to define is a nacelle, right? That cowling, right? So basically, a nacelle is just basically, in layman terms, just a circular, it can usually an airfoil shape, but it can also not be an airfoil shape, but basically it usually houses an engine, right? And in this case, our nacelle is the cross section actually defined here as a NACA 4 series airfoil, but I actually can also define segments of the nacelle, right? These are different nacelle segments. So if I show you what the nacelle is, there are actually cuts in here that have particular heights and diameters, et cetera, right, on your aircraft, right? So you can have a different interesting nacelle, which is very simple here. But if you're designing, for example, vaguely put, if you're designing a supersonic engine and it has a hypersonic inlet, right? That's very vague. You can do very interesting shapes. You can gather an idea of the flow through that hypersonic duct, right? That's as vague as I can go. Yes.
Oh, no.
Oh, yeah. So that's basically it, right? So even though this is very simple nacelle, you can do pretty good, interesting types of nacelles on this. Anyway. So the one thing that I spent a lot of time on before, drink some water. Oh, by the way, on line 638 and 639, you basically see that I appended two nacelles because the aircraft has two nacelles. But here's a Python trick. Instead of redefining the whole nacelle, Python has a function called decopy. So you just copy the nacelle, and then I just changed the Y location, right? Just made it negative, so it's on the other side of the aircraft. Okay, and then I appended that. Does that make sense? Okay, so I want to spend some time on. Okay, we got 20 minutes. It's good. I want to spend some time on the energy network because, like I said, there was a reason why I went through the presentation on energy networks, right? A lot of things have changed since SWAF days. Basically, the network itself is a class. I call it net here. And in line 645, the class is called the turbofan engine. So arcade.energy.networks.turbofan engine, right? That's the turbofan engine network, right? So there's a turbofan engine network. There's all electric networks. Some students are working on hybrid electric networks, parallel electric networks, there's solar networks, there's so many different types of networks. Turbojet, there's a ramjet network, there's a scramjet network, many different types of networks. We're going to cover the turbofan engine network, which only having turbofans. Surprise, surprise. So the first thing we want to do on our network, and by the way, the network is a class, so you can think about it that we're going to create components and we're going to append it to the network. Does that make sense? But it's kind of layered, and this is what I want to first. It's very important. This is what I want to go through. So the first thing we're going to do on that network, we're going to create something called a fuel line, right? We're going to create a distributor. Remember that this network is going to be layered. So the fuel line, we call it as in line 650, is found in arcade.energy.networks.distribution.fuel line. Because that folder distribution also has in what? What do you think it has in as well? It has in electrical buses, right? So that distribution folder has in electrical buses, it has in fuel lines, and probably some other things. But the point is that in this case, we're going to use the distributor that's called a fuel line. And the next thing we're going to do is that so we created a class called fuel line, and then we're going to create some things that we're going to add to that fuel line. So we'll create a fuel tank. So we essentially in line 656, we create a fuel tank and we append some fuel, as you can see here, right? And then we're gonna append the fuel line distributor class has, if you look here, it has already a data structure where you can put all of your fuel tanks, right? So in this case, I only have one fuel tank, but for the Concorde, if you go to the Concorde the tutorial, you will see that on that fuel line, we have 9 of them, right? It's the FYI, right? So that fuel line has only one fuel tank. So we have that. Then the next thing we're going to do is that we need to create our propulsors. We have a starboard propulsor and a port propulsor, right? So the propulsor class is called RCAIDE.energy.propulsion.propulsor. And in there, we're going to define a turbofan. We have a turbofan and all the different components of the turbofan. So the turbofan itself is actually made up of several different components: compressors, fans, high pressure turbine, low pressure turbine, etc. So we're going to create a turbofan class, which is a converter, and append and essentially define all of our components of our turbofan, from the nozzle to the ram to the compressor, high pressure compressor, low pressure compressor, high pressure turbine, low pressure turbine, etc. Right? And we append the turbofan. So you first design, so you put in the parameters, then you use this function here on 757 to finish essentially auto-populate your turbofan design. Because that data class called propulsor, what we're going to do is that we're going to append the turbofan we just created to that propulsor. Remember, propulsor is just a class that we're going to put things in there that essentially create thrust. And what we're going to put in there is a turbofan, right? If you have an electric motor and a propeller, you put those things in the propulsor as well, right? So that propulsor class. So now we have our starboard propulsor, right? We're going to append it to the fuel line, right? It's on the fuel line, right? And then we're going to repeat the same process for the port propulsor, right? To the next engine. So the engines necessarily do not go on directly to the network. Where did they go? The engine itself. What? No, the actual turbofan engine itself, it goes within the propulsor class. Yep.
Oh, no. Yeah, I was gonna say.
Yeah, it goes within the propulsor class, and that propulsor goes on the fuel line. And then where do you think that fuel line goes? No, on the network, right? So in terms of levels, and this is why I wanted to clarify, and I'll make sure we're working on a lot of documentation, but basically you have the network level, the fuel line level, right? And the propulsor level. Propulsors having things that create propulsion, turbofan engine, etc. On a fuel line level, like I said, you can have propulsors, but on a fuel line level, you can also have fuel tanks, right? It's a little bit, not convoluted, but it's a little bit detailed, but there's a reason for this definition. And it now allows you to do a lot of complex things that we couldn't do before, right? And we spent many months determining how to actually do this, and this is what we came up with. Yeah, I can tell your phone and see. So we're just gonna finish, don't worry. So I'm gonna go over the port propulsor because it's pretty much the same. Actually, what I did is that I just copied the same whole propulsor, right, using deep copy. I know how to design it again. And now we finished with the propulsor. We add the port propulsor to the fuel line, right? And then we add that fuel line to the network. And then we're done. Sorry. And they add a network to the vehicle. Okay. So now a vehicle can have multiple networks. We just only define one. And then the last, okay, you're on time. Once again, for the config setup, no. What I did is that I take my base vehicle and I know essentially use that vehicle to create copies of it. And I can change the flap settings, right? Like I said before. And the only other thing we need to discuss is now the mission setup, which I won't spend too much time on, but essentially a mission is made up of individual flight segments. You can have different types of climb segments. You can have climbing at a steady angle, claim at a steady rate. You can have accelerated claims. There's so many different types of claims. There are so many different types of cruises. You can cruise at a constant altitude but accelerating. You can cruise at a constant dynamic pressure. You can cruise at a constant equivalent speed. There's several different types of cruises, and there's several different types of descents. Yep.
Constant dynamic pressure, like
Yeah, exactly. So I wouldn't spend too much time on this, but basically you can define the altitude, start, and speed claim at, depending on the type of segment you append or you want to put on. They have different variables, right? So if the segment you append, let's say, is constant Mach number, then you're gonna have a Mach number variable there because you need to put a Mach number. You won't have a velocity variable. Does that make sense? Okay, so these are different flight segments you can do. And then the last thing here, last thing is plotting. You don't have to touch plotting. Plotting, you can just several different types of plots. There are plots that are unique for electrical stuff. There's like a plot electrical components function that plots like the motors and the batteries and stuff. You can explore the types of plots in there. So with that being said, once we define our vehicle, pretty much when you press run, it should take 1, 2, 12, 3, 4, 5, 6. About 20 seconds to run. And I ran a whole realistic aircraft and was able to essentially generate all the data that you saw. The data is on my next. The data is over here, but point is that the data is this. Don't want to bring over all again, but we ran it, and then I also wanted to plot an aircraft, so I just essentially press plot the aircraft too. So that's the synopsis of this tutorial so far. And the other tutorials are going to be similar to this, where we go over more in detail of a particular simulation. But the major thing I want to get out of here is that the networks have changed now, and they're a little bit more complicated because it allows us to do more realistic modeling. We can model now multiple fuel tanks on different fuel lines. You can model now hybrid systems that operate independently or in tandem with fuel systems or all electric systems, right? We can model APUs powering avionics that are completely separate from a fuel system that powers a turboelectric generator. This type of layering allows us to do a lot of very unique things that conceptual design cannot do right now. We're soon finished, don't worry. No, I'm just playing. I'm sleepy too. So that's pretty. Yep.
I had a question about the organization. So for like net, like there's fuel line in there, and then within fuel line there's propulsors and fuel tanks. But is there anything like in net? Are there any other folders besides, or any other classes besides fuel line?
So net is a good question. So network is a class. It doesn't really have much in it, but you can add multiple different types of distributors, right? You can have, like you said, you can have a fuel line, but you can also add an electric bus. If you just decide to create an aircraft that has one engine running on a battery and one engine running on a gas, you technically have two networks. You have a gas network and a battery network. That's if you wanted to create some random aircraft that just literally had a split down the middle, and one was just battery and one was just fuel.
Yeah.
That's how you would do it. You would just append two different types of distributors onto one network. One distributor being gas, well, the fuel line, and one distributor being the electric bus. And just to actually follow up on that, now that we have the ability to model multiple tanks now, you can have that same weird distinction, but then on that fuel line, have different types of fuel tank, different numbers of fuel tanks. It doesn't have to be one. So
Like on different distributors.
yeah. So basically, like the level of distinction that we made, or the level of granularity, yes, there are 2 more extra layers, but it now allows you to do a lot more than you would have been able to do in SWAF, which is the tool that we use at Stanford. So it's just something that we want our users to learn, and it's something that we definitely have to put more. We'll have to put more documentation on, and that's the purpose of that paper, to actually explain to people what's the purpose of what we did. All right, everyone's falling asleep, so I will stop here. Francisco and Nermit, do you have any questions?
Yes, I do. So, in this mission analysis, like, how's the aerodynamic part taken care of? Like, does it run a VLM method and finds the drag polar and then uses the drag polar? Like, how does it work?
Yeah, so there are 2 options, but we choose the first one. What we do is that we create a surrogate using the VLM. So what we do is that we create a 2D, 3D data set of Mach number, angle of attack, and I think another term, and then we query that within the mission, right? But it uses a vortex lattice method developed at Stanford, but it's based on work from McDonnell Douglas and, well, Boeing prior to Boeing, basically. Yeah.
Once you define the mission, like, does it run it every time? Or is the data already or the VLM already run and stored? So
Yeah.
you have the data and you're just querying it now.
Exactly. So yeah, you just query the data. The second way you could run it is actually by evaluating the VLM, running the VLM every time. But we don't do that because it's time consuming.
Yeah. Okay.
But there are areas where you would want to do that. For example, if you're doing a higher fidelity
Distributed propulsion.
and yes, distributed electric propulsion, right? Where you have propellers interacting with a wing, you would actually want to run the VLM every time, because the VLM feels the wake interactions, and therefore the lift distribution is different depending on the flight condition.
Have you validated this VLM model? Like, is it able to do the structural or like the fluid structure interactions and the fluid interactions both?
So the VLM model is just a model for the actual aircraft itself, or any lifting surface. The VLM model has been validated, and we have a paper on it. The reason why we wrote a VLM model is because we wanted a model that can do both subsonic, transonic, as well as supersonic regimes. And that's why, AVL can't do, transonic and supersonic. So that's what we actually had to rewrite our own VLM from scratch. And we did that a few years ago at Stanford. Yeah, it was a while ago, but basically, that has been validated for several different flight conditions, for propeller aircraft as well as for isolated aircraft, on air, whatever you want to, yeah, different types of cases.
All right, perfect. Thank you.
Yep.
Yeah, has it ever happened that it gave you like some headaches for some weird airplanes? Like, I'm thinking about eVTOLs. I don't know. There are some
We've tried to do this.
blunt surfaces, and
yeah. So sorry, go ahead, Fitness.
yeah, my question is, what if during the simulation the VLM method doesn't work properly? Is there a way to flag this or to see it?
Yeah, so that's a good question. I would say that VLMs and these types of methods don't work well in transition flow for eVTOLs, or flows where you have a high angle of attack, because essentially the assumption of this potential flow code is that the flow remains attached. Rachel, who is also, well, she's still a student at Stanford, but she is developing, she works part-time at Joby. She's developing new wake models that capture this lost in performance of aerodynamic stuff that will be implemented in RCAIDE. So that's what she's currently doing, just doing some validation on that. But she's doing a lot of propeller wing interaction because, as you know, that's what Joby does. And talking to the guys at Joby, that transition regime is something that is kind of hard to capture right now. And to capture that correctly, you probably need a higher fidelity tool, which is probably some type of CFD or LES type of situation.
Mhm. Okay, I don't want to hold you students, so I will ask you the rest of questions.
Yeah, just send me them an email. But
Yeah.
yeah. So that's our session for today. I think it's perfect timing, 4:58. Next week we're gonna cover more in depth what's going on behind the scenes, but also I want to maybe do like an eVTOL type of simulation. Maybe if not next week, the week after. I'll send an email out detailing what I'm actually doing next week. It's also in the slides from the first live meeting too, but yeah. Anyway, so thank you very much for attending. Yeah, have a wonderful weekend and get some sleep.
Thanks, Matthew.
I
Yep.
appreciate
Thank
it.
you.
Sure.
See you next week.
See you.
Bye bye, guys. Take care.